So we're back and we're going to talk about more tests for convergence. So we've got situations where we have, say, alternating series, and some of the terms are positive and some of the terms are negative. And in that situation, it can be a little more difficult to determine whether or not the series may or may not converge. However, we have a strategy where we use, where we make all of the terms in a series positive. So it's kind of like take the absolute value of all of the terms, and that's where this absolute convergence is coming from. Okay, so we say a series converges absolutely if the sum of the absolute value of all of the terms, if that series converges. All right, so converges absolutely or absolutely convergent, that's taking all of the terms in the series and making them a positive value. And so we have a theorem that we can use, because if something converges absolutely, then we can say the series converges. So in essence, absolute convergence of a series implies convergence of a series. So let's look at an example. So we're going to investigate the convergence of sine n over n squared. That series goes from 1 to infinity. So what would those terms look like? So when we are investigating convergence or divergence, we oftentimes will write out a whole bunch of our terms. We'll list out some terms. So I've got sine over 1 squared plus sine of 2 over 2 squared plus sine of 3 over 3 squared, continuing along, sine of 4 over 4 squared. Now we're used to dealing with sine of pi values, and if you consider your sine graph, it looks roughly like this, and we have an x-intercept at pi. Pi is roughly 3.14. So when I look at my sine values for sine 4, sine 5, and sine 6, those are all going to have a negative numerator, and of course the denominator for all of these is always going to be positive. So a negative over a positive is always going to be negative. So these first three terms represent a positive value, and the next three terms, 4, 5, and 6, will give us negative values. So we see we have positive and negative terms here. So since the series contains both positive and negative terms, let's look at the series if we have the absolute value of that a sub n term. So this would be the sum from n equals 1 to infinity of the absolute value of sine n over n squared. And what does that look like? So if I start listing out these terms, I have the absolute value of sine n over, and I don't need to put absolute value around n squared because it's going to be positive. So I'd have 1 squared, and I should have a 1 up here, plus the absolute value of sine 2 over 2 squared is 4, plus the absolute value of sine 3 over 3 squared is 9, plus the absolute value of sine 4 over 16. And this keeps going, but what we notice at this point is this sine 4 value is going to be positive. And so doing the absolute value of that, we've changed our sine graph. So regular sine looks like this, right? That's y equals sine x. But if we think about absolute value of sine, it's going to bounce back up. That would be y equals absolute value of sine x, right? So considering that those terms, the fourth, fifth, and sixth term, would now be positive because we have a positive in the top plus a positive, or divided by a positive in the denominator. And so since I've shown that these are all positive terms now, I can compare them. I can use my comparison test and compare it to, say, the sum from n equals 1 to infinity of some positive 1 value over n squared. And so we go back to one of these benchmark series that we have been looking at throughout our videos and our lessons here. And since the absolute value of sine n is always going to be less than or equal to 1, and that would be for all n values. Again, keep in mind what the graph of sine, absolute value of sine would look like. Instead of going down here, once it got there, it would go up, okay? And remember, sine is bounded between 0 and 1. So this is always going to be less than or equal to 1. So essentially, this series is larger than this series. So if we think about this series, the series from 1 to infinity of 1 over n squared, when we were talking about the integral test, you'll remember in the first integral test video I did, the second example in that video, we proved that this was convergent by the integral test. Okay, so this series is convergent. This series is larger, always above, sine n divided by n squared. So going back to our comparison test videos, since the larger series converges, and we can think about this visually, our larger series, 1 over n squared, we said kind of converges. If we know that converges, then the series beneath it, or the smaller series, sine n over n squared, must also converge. All right, and so we can say, using the direct comparison test, if we have two series, or the sum of a sub n and the sum of b sub n, and we know that a sub n is less than b sub n, and they're always both positive, right? So we've got the sum of two series, a being the smaller one. In this situation, our a term is absolute value of sine n over n squared, and my b term is 1 over n squared. And the direct comparison test tells us that if the larger series converges, then the smaller series converges. So what we can determine here is that our original sum, the absolute value of sine n over n squared, that series is absolutely convergent. And if a series is absolutely convergent, then we know that the original series, we can say that it is simply convergent. Okay? So we talked about also the integral test and the direct comparison test. We're using all of these tests in conjunction. So I'm going to encourage you, if you don't remember that or you missed that video, go back and look at my integral test example and then also the direct comparison test example.